Hello all. So uh, this is the first session or introductory session for our courses. Um, so welcome all. So let me see. Yeah. So we'll start with a definition of artificial intelligence from Wikipedia. Okay. So it says that artificial intelligence is the intelligence of machines or software, intelligence of living beings, primarily humans. Okay. It is a field of study in computer science that develops and studies intelligent machines. So this is what Wikipedia says uh, as the definition of artificial intelligence. Okay. Um, we will see that when we say intelligence of living beings or humans, right? It is something like very closely related to perception and understanding the world around us. So when we say intelligence of machines, it's more like uh, programming the machines to understand the world, okay, and then respond to situations based on that learned uh, intelligence. Okay. This is uh, slightly different from something like what you call the raw intelligence of living beings, right? Uh, we are not there yet. There is a lot of discussion about artificial general intelligence, AGI, and AGI taking over humans in the future, etc. So we are far from it. That is a reality. And this intelligence, what we are talking about, is more like we humans programming machines using software to fit models for various natural phenomena or process. Okay, we'll talk about that going forward. Okay, before that, before actually trying to understand how we understand the natural phenomena, etc., let's talk about some use cases of AI. Okay, AI can be used to predict customer demand. Okay, so before talking about artificial intelligence, let's talk about predicting customer demand by humans themselves. Okay, for example, in a shop in a countryside, on a countryside, etc. The shopkeeper, right? They would have learned if they were operating for some time, right, a few years, they would have learned that there are patterns in the demand for various goods. Okay, for example, during festivals, some goods, generally the sales are high because people are buying a lot and celebrating, shelling out a lot of money. That is one kind of demand pattern. And also for specific products, there will be higher demand. For example, during Christmas and all, there will be higher demand for Christmas costumes and decoration items, etc. And similarly, the Deepavali or something, there will be higher demand for firecrackers, diyas, the lights, etc. All those things. So the shopkeeper understands that over the course of a year, there are times when there are higher demand for or lower demand for certain goods and uh, the services, right? So that's the human intelligence. If the shopkeeper were very analytical, they would have noted down the previous year's sale volume for some specific products, and based on that, they would stock the goods for the current year, for the next month, etc. So the same thing we can do with artificial intelligence also, based on the historical sale volumes for various products. Uh, uh, we can find patterns in those historical time series data. It's a time series data, right? And on a day, on each day, what is the sale for each product, right? That is some time series data. So that historical data, based on historical data, the programs, that is when we say AI, it's like programs running on machines can also decipher patterns in the historical data, and based on that it can predict, for example, after 3 months of next month, what would be the sale demand, what would be the demand for a product, for a particular product in the next month. Okay, and it would be more analytical than probably if we did our hand calculations, because this is done by machines. So that way we will be able to have a more systematic or analytical um, prediction for the demand. Okay. How does this help? This helps in optimizing the supply or stock, right? We can optimize the stock such that it can meet the demand, and also we can keep only as much as goods that is needed by and thereby avoiding overstocking it also. Okay, so that's how this helps. Now let's come to another use case. Okay, autonomous driving. We all of us would have heard about this Tesla and autonomous driving, etc. It's a buzzword these days. So when we say autonomous driving, this is like various levels of autonomy are there. Even in vehicles available in India or developing countries, there are advanced some higher end vehicles where there are various features of autonomy are provided. It's not even autonomy. It's not. We cannot call it autonomy. It's rather something like you would have heard about ADAS, right? Advanced Driver Assistance Systems and all. So in this, what it does is it helps the AI is used to help the driver, etc. For example, in law, there will be a camera facing the facing forward in the vehicle, in looking at the road in front, and it can detect objects in the road, on the road, some or by the side of the road, like vehicles in front, the distance from the vehicle in front. So it can give forward collision warning, etc. That is one thing. There are other things like it can detect what do you call traffic signs, right? It can identify the signs and tell the driver that okay, there is a traffic sign there. So this helps the driver because uh, even some in low light conditions or foggy conditions, etc. Sometimes humans cannot identify the signal, the signboard, etc. But the machines can probably the AI algorithm can do some image processing and probably remove the noise or do some color correction, exposure correction, etc., and do identify the image, identify the sign, etc. So that way it is helpful. Okay, but I'm not promoting autonomy in the vehicles using AI, etc. But because that's a very risky. Full autonomy is not what I'm suggesting. In ADAS, this helps the driver, right? If some low visibility sign can be identified, the software and can be flashed on the screen for the driver or yeah, talked out loud by the software running on the car or vehicle, that is helpful, right? So that way it helps. The in the case of autonomy, there is two things. One is machine perception. Understanding that there is a sign there, or there is you are departing from a lane, etc. That is one thing, and the other thing is control. For example, if there is a vehicle in front, you can give a uh, forward collision warning. That is perception, but controlling is applying brake automatically. That is a different thing. That is control part. Uh, 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 when it is fully autonomous, that control part also comes in. But in case of ADAS, etc., that control is not there. But this ADAS also various autonomy levels are there. I'm talking about that level where there is no control, but you can get warnings or helpful information using AI. Okay. And let's go to the next one. This is more like a business case, right? The current day business case, automated customer support. So what does a customer support agent do? They understand a human agent, right? I'm talking about human agent understands the business policies and operating procedures and various information about the business. And when a customer or consumer calls, they reply back based on that their knowledge about the business, right? So and if they are not able to resolve the solution problem, they can relay it to or forward it to concerned departments within the company. So this is what the same semi-automated or structured approach to customer support can be implemented using AI. For example, current day LLMs are there, right? Large language models and generative AI you would have heard about. It's a buzzword now. So the and there is speech to text, the audio to text transcription is there. That is AI software. This was there earlier also, but with advent of newer algorithm, AI algorithms, etc., this has become very efficient. Very the correctness, the accuracy has improved a lot. Same thing, text to speech. Now we can generate almost human-like sounding speech from a written text, right, using AI algorithms. So that is the, and in the middle, speech to text, and then probably an LLM, and then a text to speech engine. This one can act as a automated customer support. And this need not be fully automated. If the customer sees that the response is not optimal, they can be given the option to file a ticket or talk to a real human agent. All these options could be done at any point of time. So this is this, but how does these things help autonomous driving and automated, semi-automated, or fully automated scenarios? It reduces the effort needed by the this one driver or a customer support agent, and in many cases the issue could be resolved automatically by the AI agent, right? In that case, the cost of a human agent is reduced, and also this can improve the customer experience, right? It can give then and there they can get a response. Otherwise, they have to wait for the human agent to come online, wait for their turn, etc. So this improves the experience also. Cost is reduced, improves the experience, and speed up the process. Okay. Uh, Now let's comes to the last one that I listed. These are by no means any comprehensive list of AI use cases or anything, but this is more like a just to give you a gist of what can be done, right? It's a very small number of examples. So generative assistance to employees. So, for example, developers or those who do programming, right? Programmers, etc. They are now able to get code. They can tell what the functionality of a particular feature is, and they can get code snippets generated automatically. Okay, and they can go through the review that code, and if there is any error they can, by the in the code generated by the machine, they can correct it, and then they can integrate that into the solution that they are developing. Okay, that's the idea. Then there is textual and visual content generation for content developers, right? So if you're writing a article, okay, long article, you can do use the generative AI or LLMs or chatbots to gather information, okay, rather than search. This gives in a nicely formatted way, etc. So it is helpful, and they can review it and include it in their article, etc. So that is there, and also visual uh, content developers. So nowadays, famous for softwares like Adobe, Photoshop, etc. They are including generative AI, generative assistants, generative tools for generating graphic content, etc. Okay. So again, this can be used to speed up the what you call work, right? Code generation, content development, all these can be sped up. Okay, people can achieve more in less time. Okay, that is the idea. Okay, uh, so now let's come back to the intelligence or machine, how machine learning or artificial intelligence uh, is that can be compared against traditional science or engineering. Okay, I'm going to compare that the AI. There's a stigma that AI is very different from what has been happening in science and engineering so far. It is an entirely new technology. That kind of aura is given to artificial intelligence. Now I want to bust that myth, so by reviewing what scientists or engineers would have done were doing earlier, and how this approach of AI aligns with that same approach. Okay, we'll go about that. Okay, so let's think of natural process, right? Some natural process, something like Boyle's law, or the relationship between volume and temperature. Okay, there is a gas, and when the temperature increases, the volume of the gas increases, right? That's a natural understanding. But what would those? I don't know whether it's in Boyle's law or not. I don't remember the name. So. People had a understanding that volume sort of increases, volume of a gaseous substance increases when temperature is increased, right? How they would have done this? They would have taken a balloon or something, filled gas in it, and measured the volume, then increase the temperature a bit, measured the volume again. So and they would have repeated this process, right? So, and what they would have done, they would have observed the values like temperature and volume. So, for example, okay, so let me uh, draw some two axes. This is volume and this is temperature. Okay, let's see. They would have made measurements, right? So, something like this. This is the temperature T1, and this is the volume V1, right? And so on, so forth. They could have measured it like this. Some measurements could have had noise. The measurement might have slightly errors in it, etc. Something like this. They would have got something like this. Okay. So here, what we are doing is there is hypothesis. That is, there is a linear relationship. It looks like linear, right? So they would have guessed that okay, it's a linear relationship. The model for this process, the volume versus temperature relationship, right? The model for that relationship, we can hypothesize that it's a linear relationship. So something like V equal to alpha T. Okay. T is the temperature, V is the volume, alpha is a constant. Okay. But we don't know what the constant is. Okay. So we proposed a model. We have made a hypothesis that this is is a linear model, but we don't know the parameter for the model. This alpha is a parameter for the model. Okay, that constant we don't know. How do we find it out? We can probably sort of it's a line, right? A linear means it's a line. So we can sort of draw a line like this. Okay, draw a line like this, and we can what we can do, how we understand that this whether this line is correct or not. We will have to measure the error. What is the error here? This error, this error, this error, this is error, right? This value minus this value, that is the error. So here it is, 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 here it is. So these are errors, and we can sum it up. Okay, sum all the errors. We can make an absolute value of the error, and we can sum it up. So that gives a measure of how good this line, this guess of this line, right? We guessed a value alpha 1. Okay, we guessed a value alpha 1. Okay, this corresponds to alpha 1. Okay, alpha 1, this red. Okay, and we got a model, and we got some error, E1. E1 we got. E1 we summed up, and probably uh, we summed up all the errors. L1 we got sigma E1. Okay, we got a error L1. Okay, now let's think of another model. Okay, slightly different model, slightly different alpha. Alpha 2, let's talk about alpha 2 we guessed. because this looks slightly off, right? All the points are above this. Almost all the points are above the line. So we can guess something like this. Okay. So it looks like this is slightly better, right? Let's see the errors. Here now the errors are like this. Okay. So now the errors are like this. Okay. And it looks less, right? The errors, smaller errors are there. These vertical lines are smaller. Okay. So we got uh, another loss, that is L2 equal to sigma E2. Okay. E is the small value, the single values, these errors, and L2 is the sum. Okay, we basically have to take the modulus of it, because absolute value we will take and we'll sum it. Okay, so now it looks like L2 is less than L1, right? L2 less than L1. So we say that, okay, alpha 2 V is equal to this alpha 2 is a better guess. Okay, so we got maybe we would have started with, if we really had no idea about where to draw the line, we could have started uh, somewhere like here also. Okay, something like this. Okay, then the error would have been very high. Then we went to red line, then we went to green line. So finally, green line is sort of a good guess for the model. Okay, so the parameter we guessed, we got a optimal parameter alpha 2. Okay, and in machine learning also similar thing happens. We first hypothesis a model. Okay, model for a process, and we make observations, that is we collect data for the same for the process, and we try to guess the parameters of the model, and then we measure errors based on that model. If that model is the actual one, what would be the error when compared to the actual observations? Okay, so that error we take, then we sum it up and take a come up with a number, loss number, and based on the loss number, if loss is the idea is to bring the loss down as small as possible, right? It might not be zero because there is noise, but we want to reduce the noise, or minimize or optimize the noise, minimize the loss, reduce the loss. If the loss is minimum, that means that's a good model. Okay, so we have to minimize the loss or optimize the loss. Okay, this optimization process is called training. Okay, now I'll show you some a demo also for the same. Okay. Okay, so here is a demo for what we drew on the screen earlier. So don't worry about the code snippets here. Just think about the figures only. Okay, this text and figures. Okay, so let's see. The first we will have noisy observations for a linear process. Okay, this is the noisy observations. And what is a linear process? Y equal to mx. We talked about volume and temperature, right? This could be volume or temperature, or it could be speed, and it could be displacement and time. S is equal to D, displacement D is equal to speed times time, amount of time traveled. Okay, that is Newton's law or something we would have heard about, right? So if constant speed is there, the distance covered would be speed times time. That will be the displacement or the distance covered. Okay. Similarly, another thing could be the voltage across a conductor. It is equal to V equal to IR. We would have heard about Ohm's law. We would have heard about, right, in our school, higher secondary, etc. So there also it is like a linear relationship. Uh, uh, V equal to IR. R is the resistance, I is the current through the conductor. If a current I is flowing across a conductor of resistance R, the voltage difference across the conductor will be V. Okay, so that is a linear relationship. The constant is resistance R. Okay, same thing here. Y is here. In the case of volume and temperature, V is represented as Y here. Temperature is represented as X, and alpha we talked about is represented as M. the parameter of the model y equal to mx. And in this case, let's draw a generate a process where the slope m is we call it slope, right? When the line, right? When there is a line has a slope, we would have heard about, right? That is m. This m parameter m is taken as 11.4, and I have generated data like this. So I'll show you. Don't worry about the code here. So I've generated a this is the x axis is x, y axis is y, and these are the observations. Okay. Now, how will you fit a model, linear model to it? Y equal to mx. We guess m, just like we guessed the slope. We drew different lines, right? Yellow, red, and green lines we drew earlier, right? So, how did we draw? A line is specified by the slope, right? Uh, if it is going passing through the origin, the slope is what determines the line. So, we guess that slope or parameter for the model m, and plot this line y pred equal to mx. Okay, y is the original observation, y and x, and what is the line that we have guessed? Y pred equal to mx. Okay, I'll show you. So I'll start with something like uh, some 22 or something like that. Okay, so it's off. We guessed a value of m as 22, m param this value as 22, and we drew a line. Okay, after drawing the line, we calculate the loss. Okay, what is the loss here? It is very high, 15,000 something loss is there. How did we calculate loss? We summed up the errors. What is the error? The distance of these points from the vertical distance of these points from this line. Okay, that is the error. And we summed up the errors and we got a loss. Okay, so first thing is guess the line, guess the parameter of the line and hence the line, and then plot the line and calculate the loss. And next step is plotting the loss curve. Okay, so I have drawn a curve here. Okay, this curve is like for the parameter m, right? This x represents the x-axis represents the parameter m. For various values of m, what is the loss for this observations? For the given observations, what is the loss here? Okay, if m equal to m1, say 22, for that this is the loss. Okay, we will get the loss like that. So suppose let's do it 20. It has gone out of the bound. So 20. Let's see. So we can see 20. If 20 is m is 20, this is going to be the loss. Something like 10,000, 12,000, something like that. Yeah, it is around 10,000. Okay, loss is 10,000. So we got a loss like this. And then what we will do, we looked at the loss, right? Loss, and then refine the guesses of m. Okay. How did this is calculated? Y represent the observations and repeatedly guess value of m and calculate y pred equal to mx. What is y and y pred? What is the difference? Y is this actual observation, blue dots, and y pred is the guessed one. Okay, the line we drew, right? That value for this one, this is the value of y pred, and this is the error. We saw that in the earlier drawing on the screen, right? So that is that. Then what do we do? We calculate y pred minus y, and loss is sum of those errors. You can think of it like that. In this case, what I've done is I've taken the square of the errors and summed it up. Okay, and then average the average the loss. So average means I sum the squared errors and divided by number of observations. Okay, that's how I arrived at loss. Okay, now what we do, we saw that it's off, right? How do we bring down the loss? If we move to the left, right? If we move to the left or something, it might be the loss might come down. That's how the loss curve. That's what the loss curve says. So let's do something like, let's guess 2. 2 is less than 20, and how does it look like? Oh, it came here. Okay, opposite side. So the error has increased. Okay, 2 is not good. So we have to move to the right. We should not go as far as 20, but we should move to the right. So let's see. 16, let's try. Yeah, 16 is a better guess here. And the error is only 3,000. The loss is only 3,000. And you can see here, The error is here, the loss is here. It is around 3000. That's a good one. So, but we have to go to the left, right? Because lower value is required for m. Then only loss will be less. So let's try 8. Okay. What happened? Okay, the line came to the opposite side actually, but the loss has come down. It was 3000, now 1700, 1700. Okay, and it is here. So yeah, now it looks like it between 8 and 16. Okay, now what should we do? We can guess something like 10. Shall we guess 10? Uh, 10 means okay, now it is closer, and the error is only 454. Okay, now we are getting closer, and here also we are getting closer, right? Let's see. Now I think we have to still move to the right, right? That's what it indicates. So let's try 12. Okay, 12. Okay, it's pretty close, but it has gone to the opposite side. Most of the dots are below the line. Okay, error is very small, 264 only. But it is to the right. Okay, now we have get an idea that we have to slightly, it is between 10 and 12. So let's try 11. Okay, let's try 11. Mm, Let's try 11. Now the error is, yeah, slightly less, 227. Let's see the plot. Okay, now the most of the dots are above the line, but it is very close. Okay, now probably it is between 11 and 12. So let's try 11.5. 11.5. Okay, now we get more or less close, very close. The dots are distributed above and below the line, more or less evenly. And what is the loss we got? 212. That is very less. Okay, very less. It will not be zero because there is noise here. We cannot not all the observations lie on a line. That's why we are getting a non-zero loss, but we are close, right? And we know we started with 11.4 and added noise to it, so we arrived at a good guess. Okay, so what this process, right? Guessing and calculating the loss and repeating that process, that is called training in machine learning. Okay. This is same what our earlier scientists or engineers would have done. They made observations, collected data, or made observations, and they made a hypothesis of a model, whether it's linear. Some cases it could be quadratic, right? Quadratic means instead of y equal to mx, it could be y equal to mx square plus m2x, something like that. So it will be quadratic. Okay, or it could be even big more. It could be y equal to m1x plus m2x m2 m1x1 plus m2x2 plus m3x3 multilinear. Okay, it is linear, but multiple variables are there, like that. It could be, or it could have many number of parameters. The model could have many number of parameters also. In our y equal to mx case, there is only one parameter is there. In multilinear case, there could be n parameters like m1, m2 up to mn. N parameters could be there. Like that, that's the idea. Okay. Mm, Now, yeah, we will just see this process, repeating guessing process. We started with some 2022, then okay, I'll tell you. These are the values: 22, 2, 16, 8, 9. We didn't go to a 9 and all, but almost we did all those. Okay, so we got initially it was like here, then we moved here, reduced the loss, but switched to the opposite side, again switched to the opposite side, then came here. Then we got an idea that we have to increment slowly. Earlier, our jumps were bigger. Now slowly we are jumping, and finally we got the this point. That is 11.5, which is very close to the original value, right? Uh, Now we will plot that, right? We plotted that here, 11.5. Okay, so this is what I wanted to show you. This is very more or less same as machine learning only. Okay, this process, this is the process of machine learning, machine learning training, what we call, right? This is what the process is. Okay, so now let's move on. Okay, now let's move on. So yeah, this we already saw. All this process we saw. We saw the demo. Now let's come to an example use case. Okay, we talked about line fitting, right? In that case, it was like y equal to mx. Okay, that was a model that we are fitting. Now let's come to a real use case, that is traffic sign recognition. Okay, there is a forward-facing camera on the vehicle which records the video, and in the AI software running on the vehicle detects objects in the frames of the video, and it recognizes the traffic sign. Okay, by classifying the sign into the correct category, such as a stop sign, speed sign, parking sign, school zone, etc., depending on the standards used in the region. Okay, different India might have some particular signs standard for signs. Some other country might have some other standards, etc. Okay, so now in this case, what are these y and x's? Okay, and what is m? Okay, we will see that. Okay, now we know that there is a finite number of categories that the system has to choose from. So this is a classification. Okay, we have to classify. Given an image, suppose there is a stop sign image is given. This image is the x. Okay, input x is image. Then there is an AI model or a function. In our case, the function was y equal to mx, or the model was a linear model which is y equal to mx. It had just one parameter m. In this case, there will be many parameters, m1, m2, m3, maybe thousands of parameters it might have, and then output is y is a number, okay, category number, okay, label or a number. Okay, we can number labels, right? Stop sign means 3, or school sign means 7, or speed sign 30 means 8, speed sign 50 means 9, things like that. You can put a number. So y is that number, label number, and x is that input image. Okay, in how can it be a number? Input image can be split it into individual values, right? It could be a 32 by 32 image. So 32 into 32, that is 1024. 1024 pixels are there. You know, right? Pixels in the image. So each pixel can have a value. Okay, number. Okay, that's a number. So that how the x is a vector. X has values x1, x2, x3, x up to x 1024. If it's a 32 by 32 image, black and white image, not black and grayscale image, then 1024 x's are there, and each x will have a value between 0 to 255, something like that. So that's what the input is, and output is a category number. Okay. Mm. So what we need to do, we have to come up with an AI model or a function for which the input is x, which is the image of a sign, and output is the category y. Okay, and what are the observations? We can collect many photos of signs, right, and label them. If we get the stop sign, we label as stop sign. If we get a what do you call roadblock, or we say that there is a bridge or something, we name it as bridge. Or if there is a right turn, we name it as right turn. If there is a people at work, we name it as like that. That is labeling or numbering. Okay, so we can collect lot of images and number it or put category or classes for that, class number for that. So this is called data collection or curation, or this is same as observations. Okay, we made volume and temperature observations, right? So this is same, data collection or making observations. Okay, then what we do, we can feed our function, the AI model. It has tunable parameters. Y equal to m, in y equal to mx, we were guessing the parameter m, right? So that is the changing parameter. It's a tunable parameter. Okay, so same way, our bigger AI model also will have many tunable parameters, and we can input it with one photo after the another. For the sake of simplicity, let's put it like that: one photo after the another, photo of sign, traffic sign after one another, and we can look at the function's output. Okay, and adjust the parameters of the model or the function till we get good results. Okay, that is the idea. So what do? We have a model with lot of tunable parameters. We input a image, we see what the output is. Based on the value of the output, we modify the parameters. Okay, and we repeat this process until we get good predictions or good classifications. At the end, we should get something like at least 90% of the images we input, it should say the correct class or the label, right? Then we say it has that model has 90% accuracy. Okay, if it has very high accuracy, 99% accuracy and all, we can probably say, okay, we have a very good model, we can maybe productize it and we can put it in, make that model is nothing but a function, right? We can write it as a program and we can make it part of the ADA software running on the vehicle. That is the idea. Okay, now we go to a demo for this. Okay. Okay, let's see. Okay, we have got a program here. Again, don't worry about the lines of the program. Okay, don't worry about the code. I'll just run it. Okay. Uh, this is a little time consuming one because now the model is big, right? So don't worry about any of this. We are loading the data here. The loading data is successful. Now let's see. Okay. Yeah, so there are 12,630 images there. Okay, we have collected, and for each image there is a label. Okay, length of ground truth label is 12,630. Okay, that is the idea. And number of classes 43. We will see which are those 43 classes. Stop sign, school zone, etc. We will see. Okay, let us see. So these are the classes. Class 0 is speed limit 20. Class 1 is speed limit 30. Class 2 is speed limit 50, and so on. This is what I told. In low light conditions, humans might miss the sign, right? But the machine can actually do some image processing, increase the exposure, etc., and predict, understand it better. Okay, so this is speed limit 60. This is some speed limit 70, speed limit 80, and so on. End of speed limit 80, speed limit 100, 20, no passing, no passing over for vehicles over 3.5 metric tons. Right of way at the next intersection, priority road. This is priority road. This is yield, stop sign, no vehicles, and so no entry, and so on and so forth. Okay, there are such some 43 classes like that. Okay. Now let's see. Okay. Don't worry about any of this. This is called data augmentation and all, but don't worry about it. We will cover that in the classes. Okay. Sessions we cover next in the actual regular sessions, right? Going forward, we will cover all those. Don't worry about any of these. Then, okay, we made it was color images. We made it into grayscale images. Then, okay, this is the model. Okay, the name of the model is LeanNet. Okay, and it has so many parameters. We had y equal to mx, only one parameter m. Now we have something like you can see 64, right? 64 is there. There is 256 is there. Then there is 1024 is there. Then again 120. So there are some 2000, around 2000 parameters there. M1, M2, M3, M4, M5, etc. up to M 2000. Okay, not exactly 2000, so around 2000 parameters are there in this model. Model name is LeanNet. Don't worry about any of this. We will come back to this in the regular course. Okay, now let's see. Yeah, I think I ran this. I ran it again. Yeah, then okay. Don't worry about any of this code. Okay. Now this is a training step. Okay. Um, here, the optimization, right? Tuning the parameter. That is what is happening now. Okay. It will take some time because this is a you saw, right, around 12,000 images are there. So this is one iteration. Okay. After one iteration, what happened? The accuracy was only 21%. 0.21 means 21%. So around if you input some 100 images of the signs, only 21 of them it was able to correctly guess. And after the second iteration, right, iteration of tuning parameters, it was the accuracy increased. Now 34% of the signs it is correctly able to correctly identify. Okay. I have set some 30 iterations here. So we will see it is keep on increasing. So that's the idea. And meanwhile, let it complete. I'll go to the slides once again. Okay. Um, uh, we will come back here once the 30 iterations are complete. Okay. Okay, so we will come back to the example use cases that we discussed. And here we will see what are the X's and Y's in this case. Okay, when we predict the customer demand, right? X is the historical sales data till day D. Okay, for if today is the day D, it means all the sales data for each day in the history. That is like yesterday, what was the sales data for each of the products? Day before yesterday, what was the sales data for each of the products, and so on and so forth. That is X. And what is Y? What is going to be the sales for a product tomorrow? Okay. This is just an example. Today, if D is something like today, and we can guess it for next month also. Okay. So that is the idea. X is the historical sales data, and Y is the what is going in the future, what is going to be the sales. Okay, that is why. In the case of autonomous driving, this is just one example. Okay, this customer demand sales data could be one thing, or it could be in power distribution, right? In electricity billing, in some apps, some of the some regions have apps where it tells you what is going to be your bill next month based on your usage, previous usage. Okay, that is again this custom demand forecasting. Okay, demand or time series forecasting. Okay, bill the value forecasting, right? How much power you would require in the next month. It is guessed based on your past usage, and based on that it will tell this is going to be your bill. Okay, next month. So this is just an example. Okay, and autonomous driving, if we take the sign recognition or object detection, X is the images captured by the front camera. Okay, and what is Y? Labels of objects in the image. What could be the labels? The traffic signs or the vehicles in front, etc. That could be the Y. Okay, the labels of the objects identified in the image. Okay, in customer support, what is X? Sequence of n words, that is X, and word at position n+1, that is Y. That is, if there is a sentence like a quick brown fox jumped over a cat or something like that, then a quick brown fox. Okay, that is the n words. Next word, n+1 word, that is Y. Okay, a quick brown fox, that sequence of words represents X, and Y is the next word, guess for the next word. Okay, uh, if what is the probability of the next word being jumped? Okay, quick brown fox, next word, what is the probability of the next word being jumped? That is Y. Okay, for jumped, the probability could be very high, probably something like 0.7 or something. Uh, for something like uh, uh, one, and that's another English word, right? A quick brown fox, one. That probability could be very less, 0.1 or something like that. So that is why. Generative AI also same thing. It's a sequence of words, generation of words, right? That is what is done in generative AI. Okay. Uh, so same thing in visual one also. What is going to be the value of the next pixel, given the pixel values previously came. Okay. So like that. Okay. Now let's see. Now let's go back to the graphic sign training. Hopefully it is done by now. Let us see. No, it is not completed, but you can see the accuracy has improved, right? Now 86% of the images it is able to correctly identify. Okay, let's wait for a couple of minutes. We will discuss your preferences, etc. Now. Okay. Uh, Let me go back there. Okay. So till this gets completed. Okay. So we will discuss these things, your years of experience. If you are not comfortable discussing that and all, you can skip that. When you talk about it, when your turn comes, you can talk about the years of experience you have, and you may skip that also. And you can basically you can think about this, okay, in your head. Current level of knowledge in math and programming, okay. How much knowledge you have in math and programming, okay. You don't need any experience. I will actually cover the math and programming required for the content of the course, okay, at the start. So don't worry about that, but just think about it. And based on that, you can decide, like, do you want to go for the engineer stream or leader stream? Okay, leader stream will be more into use cases and different AI algorithms which can be used to solve those use cases, etc. And also in leader stream there will be more discussion about your projects, subject to confidentiality things. You can discuss if there are open things that you can discuss in the class. You can discuss that, your projects or business use case, etc. And we can see business area, etc. And we can come up with use cases where AI can be applied and solve the problem. Okay, so that is at least 20% of the time will be devoted to that. Rest of it will be discussing various types of AI algorithms and the use cases which can be solved using them. Okay, that is the main idea. In the engineer stream, we will discuss the use cases briefly, and we will see which we will learn about many AI algorithms which can be used to solve those use cases, and we will also go a step further in understanding how to implement those AI algorithms and deploy it in production. MLOps also we will discuss. Okay, but leader stream will be more focused on higher things like business use cases, etc. That will help you in uh, creating project proposals, etc. Okay, to grow in your career. Okay, then then you can think about how much time you can devote per week. Okay, basically I am expecting some 2 to 4 hours per week for attending classes, and around 2 hours for doing take home exercises, some programming exercises, etc., especially for the engineer stream. Okay, so leader stream also I'll give you some exercises in listing down based on your business area, listing down some use cases, etc., and then thinking through AI algorithms that is studied so far, and coming up with methods to solve those use cases. Okay, so that is the idea. Then the next thing you have to consider is your time zone and what class timing would be comfortable for you. Okay, so I see there are people from India, Europe, and US. So I assume that the evening time, 7 to 8 or some 8 to 9 p.m. IST would be an ideal. That's what my understanding is based on the feedback I've gotten, the time zone you people are in. Okay, India people are there, and US and Europe people are also there. Okay, so I think evening, then 8 to 9, etc. 8 to 9 p.m. IST. That would be an ideal time. That's what my guess is. And mostly the classes will be only on weekends. Okay. And I will record the classes also, so that if at all you miss a class, I will send it to you. Okay. Personally, I will send it to you. Okay. Now let's go back whether it's done. Okay. So yeah, now it's done. Now you can see the accuracy is like around close to 90%. Okay, 99% of the images it is able to properly classify. Okay, now let's see. And now we will see. Mm, we will download some images from the web. Okay, it is already downloaded and saved here. Examples web images. So this is not used for training. Okay, some new images I've downloaded, and let me read in those images. So there are 5 images, okay, and this again 32 by 32 images. Okay, now let's see. These are the classes. Okay, these are the images and classes. 25 means men at work. This one is yield, or this is priority road, etc. 30 speed sign. So these are the numbers, the class numbers for that, label numbers for that. Okay, now let us see. Okay, so yeah, these are the images, and let us see how it is able to predict. Okay, okay. Um, okay, I think I didn't run this. Okay, there is some error with the intent. Okay. Okay, so accuracy was 80 percentage. It got, I think 5 images are there, so 4 of them it got correct. That's what it is. Now I'll print the probabilities also for each confidence level. Okay, the first image, right? It had one probability one. With probability one, it predicted 25. That is road work. Second one also it predicted with probability one, close to one, yield. This is the image. Third one again with probability one, it predicted like that. The fourth one, it predicted as pedestrians. Okay, and the confidence was 76 percentage. Okay, but it was a wrong answer. It is not pedestrians. So that's the one which went wrong. So this is a pitfall of this one, machine learning. You can see the probability is less compared, the confidence is less compared to the previous guesses, and it came wrong also. Okay, then the last one also 99 percentage accuracy. It was able to say it is the speed limit 30. Okay, so this is the idea. Um, yeah, so that's all I wanted to share in this introductory session. Okay, I'm looking forward to hear from you, and uh, if you decide that you can register, you can let me know. I'll share the bank details, etc., for paying the fee and registering. And I'm hoping to start the sessions, regular sessions, by April 1st week. Okay. Okay. Thank you. Bye.